Welcome everybody to a new colloquium. The speaker of today is Amnon Besser from Gurion University and currently visiting Boston University. And he's going to talk today about p-adic method for solving Diophantine equations.
Okay, so thank you very much for the invitation to speak here. It's been a while since I've been in Montreal, and it's really a pleasure. I'm part of what I'm going to talk about today is joint work with Padma Srinivasan and Jan Stefan Muller. So I want to start by sort of pointing out that the problem of solving equations in integers or rational numbers is an ancient problem. It might be the oldest problem in mathematics. So examples is Fermat's last theorem. And a very recent example, sort of just as an interesting point, is you can ask for the solutions in integers for all the for every k from 1 to 100 between finding this as a sum of 3 cubes, and all the ones were solved except the last one, which was solved I think 3 or 4 years ago, and that was for the number k equals 42, which we all know is the meaning of life. And in order to get the meaning of life, you needed all these big numbers. Okay, and the technique here is just a sophisticated massive search. So there's nothing deep about it. So it's sophisticated in the sense that you don't just look on a big box, but you have some kind of a preconditioned way of looking for specific numbers. And the problem that I want to discuss today is sort of just mostly restricted to the simplest case, which is curves. So you just have one equation in 2 variables. So even more specifically, a lot of the cases we treat are cases of hyperelliptic curves, y squared equals fx. And but in general, one treats varieties, which are any number of equations in any number of variables. And the curve over C is a Riemann surface. It's just a surface with a certain number of holes, and G, which is an invariant that's going to show up many times, is the genus, which is the number of holes, and there's something which we'll discuss later on. It's the number R, which is the rank of the Jacobian. And in any case, given such an equation, rational numbers, we want to find xq, which is all the rational solutions of the equation. Okay, so our techniques are basically p-adic techniques. I'm wondering if there's something in the top that we're missing. Maybe there is. No, I don't know.
I have to exit the screen. No, it looks
okay. Yeah, I guess it's okay. Yeah.
No,
okay. Yeah, I think I must have missed them. Okay. So anyhow, the p-adic numbers. So we're going to use the p-adic numbers, and the p-adic numbers are a completion of Q with respect to the absolute value. So if I have a number, rational number written as some power, possibly a negative power of p times a over b, where a and b are not divisible by p, then the absolute value is p to the negative r, which means that numbers are close if their difference is divided by a large power of p. Okay, and p-adic methods, all the p-adic methods that we have for finding solutions to equations go in a similar path. You pick a prime, which can usually be fairly variable, and you consider the rational solutions inside the solutions in this bigger field of p-adic numbers. And this set of solutions in the p-adic numbers is considered well understood, although it's quite big. And the reason is something like a theorem called Hensel's lemma, which says that if you solve, basically, roughly, if you solve the equation modulo p, so up to multiples of p, then you solved it. And then to solve that, you just need to sort of check all the possibilities on numbers between 0 and p-1. So that's a finite problem. Once you solved it, you basically have the solutions in QP. And then to get the Q rational points inside of the QP rational points, what you want to do is you want to find a function f on xqp whose zero set is finite and it contains a x cube. And I mean, this is maybe not saying enough. If the function is analytic, which it usually is, it means that there's a finite number of solutions. And then to actually find them, you really want to be able to compute this function. Okay, so several cases where this is discussed, where this is treated are as follows. So the whole subject maybe starts in 1941 in a paper of Chabauty, where he proves that if G is greater than R, so the genus is greater than the rank, then he proves that XQ is finite. And as you can see in the second thing, this predates one of the famous theorems of the 20th century, the theorem of Faltings, where he proved Model's conjecture, which was that anytime G is greater than 1, XQ is finite. But the difference is that this Chabauty method is effective and also quite computational. You can really get what the rational numbers are, and whereas Faltings is completely ineffective. Coleman actually shows that the method of Chabauty gives very good effective bounds on XQ. So in many cases, the bounds that are provided by Chabauty's method are just sharp. So all the points are accounted for by this method. And various people have done computations using this Chabauty method. Right? It's too long a list to actually do. Okay. So now there's Kim's non-abelian Chabauty. And then I also put a picture of Kim and also a picture of Robert Coleman, who's kind of the starting point of a lot of this stuff. But Kim in 2005 started using fundamental groups for trying to generalize the Chabauty thing. And then in theory, using certain conjectures, Kim can sort of prove that you always get finiteness. And then we're really lagging behind in terms of algorithms. There are only finite number of cases where you really get some sort of algorithms. And I'm sort of proud to point out that two people who are really leading the field, and this is my two colleagues at Gurion University, Shai Dan Cohen and David Corwin. So anyhow, that's one direction to go. And then there's the method of Lawrence and Venkatesh, which is even more new, and that uses somehow Galar representations. The advantage is that it provably works in general. It actually gives an alternative proof of Model's conjecture, but a different disadvantage is that it's probably not practical. It's my understanding is that it's not something that can be easily improved. It's not an algorithmic problem. It's a really problem where you sort of the structure of this is that you'll be able to find this, but the work will involve sort of checking too many cases. Okay, so now I'm going to switch to this what should be kind of like a subfield of Kim's work, but it somehow uses he sometimes uses slightly different techniques, and that's a thing called Quadratic Chabauty, which in some sense I sort of helped start, as you can see with Balakrishnan and Muller, or two of the people you can see here, and so anyhow, this is a method that sort of initially started by doing just finding integral points on hyperelliptic curves when R is G. So just going almost the least amount of steps beyond what Chabauty can do. So Chabauty can always deal with G greater than R. So the first case where it can do is R equals G. And in this case, we've been able to treat integral points, or not even rational points, and on hyperelliptic curves, which are very simple curves. And the method uses p-adic height pairings, and you'll see in the end where I'm going, where this is sort of generalized using kind of more general p-adic heights. But in any case, then Balakrishnan and Netan Dogra, who's a student of Kim, was a student of Kim, have been able to show that you can actually get, using an extension of this method, get rational points when you have more sort of correspondences. So if there's some more algebraic data on the curve, then you can actually get all the rational points. And the method there was sort of a mixture of Quadratic Chabauty and Kim's methods. And then these 5 people here, Balakrishnan and Dogra and Stefan Muller, and then this is Jan Chutman, and then this is Jan Vonk, who I think was here, so maybe some of you know him. All of these were able to use this to solve a long-standing problem, important problem. They got a publication on in the Annals for that, and that is they found the rational points on the cursed curve. And I'll spend some time explaining who cursed this curve and why. So yeah, and that's actually coming. So this is slightly about the cursed curve. This guy is not a mathematician, is a Dutch football player from the 70s, and he used to have a really vicious kind of penalty kick that would curl very much, and it used to be known as the cursed curve in Dutch. So this is one interpretation of what's the cursed curve, and it's another interpretation of the cursed curve, which is some graphics which was produced by Jane Balakrishnan. I actually don't know how she does this and what it actually represents. But then, if we want to be even more concrete, this is the cursed curve. So it's some equation, and then if you, I don't know if some people are so good at number theory that they sort of immediately see some relation between the numbers. I don't think I ever actually kind of absorbed all these numbers, but there's some meaning to this curve, and I'll try to explain at some point a little bit about that. And so it's a modular curve. And what are modular curves? Modular curves are algebraic curves that are parameterizing elliptic curves with some extra structure. So what is an elliptic curve? An elliptic curve is basically some equation y squared equals fx, where the degree of f is 3. There's some minor condition about having this distinct zeros, and that's the famous sort of picture of an elliptic curve. And what this diagram is supposed to show is that elliptic curves are distinguished by the fact that you can sum. There's a formal way of summing up points. So you take 2 points on the curve and you pass a line between them. And because this is a degree 3 equation, they're going to intersect the curve at the 3rd point. And if for some reason, see, this curve is sort of symmetric with respect to y. So if y is a solution, negative y is also a solution. So for some reason, the sum of P1 and P2 actually goes in here. So it's not the intersection point, it's actually the negative of the intersection. And that makes elliptic curve the simplest example of abelian varieties, which are varieties which are also groups. All right, so see, abelian variety is a variety and a group. And then there's a general theorem, which is due to someone we already mentioned, Mordell, the conjecture, and then Weyl's Hermian figure that will also show up later. And that is for any abelian variety over a number field. So if you have something of that sort, a variety, so defined by equations in certain amount of variables, and also has this group structure over a number field, so all the coefficients are in a number field, then the set of all solutions, which is now a group because the rules kind of tell you how to add them, this group is actually a finitely generated group. That was a very famous theorem from the 20s. And then in particular, if I look at all the points which are torsion points, so when I add them up with themselves, I eventually get 0. This is a finite. For example, if I look at the elliptic curve y squared equals fx, right, the one that we've discussed, there's the two torsion points are just all the points where the y coordinate is 0, or the point at infinity, which I didn't mention. Well, all this story, there's a point at infinity, which is sort of somewhere here, and you see it if you take a point like here when y is 0, taking the sum of the point with itself means taking a tangent, and the intersection point of the tangent, in this case, the tangent sort of goes directly upwards. It only intersects at infinity somehow. So there's an additional point at infinity which actually serves as the 0 point of the elliptic curve. And so two torsion points are the points where y equals 0. And there's a very famous theorem by Harvard mathematician Barry Mazur that says if you have an elliptic curve defined over Q and you have a point of order n, so you add it up with itself n times 0, and it's defined over Q, so the coordinates are also in Q, then this can only happen if n is less or equal to 10 or n is 12. So it limits in a very strong way the number of torsion points that an elliptic curve over Q can have. And modular curves are, as I said, parameters for elliptic curves with additional structure. And the simplest maybe case is this lambda line. So it's you take P1 and you throw away 0, 1, and infinity. And what you can do is you can parameterize elliptic curves with a fixed labeling of all 4 points of order 2. And you get, how do you do this? You take the parameter lambda, you write the elliptic curve y squared equals x, x minus 1, x minus lambda. And now the points of order 2 are 0, 0, 1, 0, lambda 0, and the point at infinity. So I've labeled all the points of order 2. So that's a simple example of a modular curve. And there's a more general notion of an elliptic curve, of a modular curve, which is called yn. So this classifies elliptic curve with a fixed point of exact order n. And this, just like this thing, it's not, in some sense, non-compact. You moved some points, and so to make it compact, you have to add some cusps. So these cusps don't correspond to actual elliptic curves; they're just there to compactify. And in that sense, and this is sort of ties up this interlude into modular curves with the quest for rational points, is that the modular interpretations of Mazur's theorem, it's not just the modular interpretation, it's really actually how he proves the theorem, is that except when n is 10 or n is less or equal to 10 or n is 12, the only rational points on x1 n are cusps. And then what's the cursed curve? So it's another kind of modular curve. It's kind of technical to explain exactly what it is. And it sort of comes up in a long list of modular curves of this type, and techniques similar in part to techniques of Mazur were used to kind of look at all the rational points on these curves and usually be able to say that they are only cast as rational points. And the people who did that, Yuri Bilu and Pierre Parent, they were able to do this for all curves of interest in a particular class, except one. This is like the non-split Cartan in the case for the case n equals 13. So whatever that is, that was the one single curve they couldn't handle using their technique. And so what they did was like 5 years old, they just decided to curse the curve. And so since then, it was known as the cursed curve. But now, of course, the curse is lifted because these guys that I listed before were able to find the rational points using these p-adic techniques. And I said, for me, this is really satisfying because it's one thing if you say, okay, I can solve this equation using these techniques, because a lot of people are trying to find rational points. And this is a case where people have thought really hard about finding the rational points in other using all other methods, and they failed. So this is an indication that this method can actually do something that other people can. Okay. Okay. And I want to spend just a little bit of time talking about the method of Lawrence and Venkatesh, which is even newer. So the idea is that I can actually make any curve parameterize other varieties in many ways. And what they do is they somehow use that to parameterize as a particular kind of varieties, and they get out of that representations of the absolute Galilean group of Q bar over Q. Now, there's a long theory of how to get out of varieties representations, but the simplest way of understanding how this might happen is you look at the points of the elliptic curve, the two torsion points, say, of the elliptic curve, and these are just a vector space, actually of dimension 2 over the field with two elements, and the Galois group acts on them, because if I take one torsion, if I take these points and I apply a Galois automorphism, I get the same kind of point. So that's a representation, and really somehow that's the kind of the really starting point for actually associating representations to varieties, but it gets much more complicated than that. And then really deep theorems like theorems of Faltings that were used to prove Modell's conjecture tell us that somehow once you kind of see what type of varieties you get there, you can actually say that there's only a finite number of such representation that can occur. The reason this is not so effective is that the number is finite, but it's huge. And so now I can look at and I have to sort of do something p-adic. So I kind of restrict further from Galois group of Q bar over Q to Galois group of QP bar over QP. And when I do this, it turns out that this map is somehow locally analytic. And so now I'm supposed to hit with a local analytic a finite number of targets, and that gives me finiteness. But as I said, it's probably not effective. Okay. So now I want to explain Chabauty's method, and for that I need to do a small interlude into Jacobians and Abel-Jacobi maps, which is a classical. Well, starts out as being something classical. So let's consider X over C a curve, and I can look at the holomorphic one forms on the curve, and this space has dimension G, and I fix a point on X, and then you have abelian integrals. So this is teaching multivariate calculus now, so it's like it's close to home. So you take a differential form and you look at the integral between the fixed base point and P of this form. And now, unfortunately, it's not a conservative field or anything. It really depends on the path. But two paths give you a closed path, and you can just quotient out by the integrals over all possible closed path, which is given by the first homology group. And so what you end up is with functionals on differentials, mod functionals that are given by H1. And this turns out to be a nice sort of choice. It's a dividing a complex vector space by a lattice. So you get this map. This is called the Abel-Jacobi map. There are various generalizations of that. And this map is sort of linear, or it's additive, so you can extend this to sums of points. And in order to make this independent of the base point, you usually restrict to sums of points where the sum of the indices is 0. So you have this. This is a theorem of Abel that alpha of d is 0 if and only if d is a divisor of a rational function. So divisor of rational functions mean you take a function on the curve, and usually this function will hit infinity and 0 at certain points, and you sort of take these 0 and infinity according to how many times it's basically hit. So if it has a 0 of high order, you take this point with this order. If it has a pole of high order, you take the point with the negative of that number. And then Jacobi actually shows that this is alpha is actually onto J. And so that means that you can actually write this J as some formal sums of point mod rational the divisors of rational functions, and that's when you can say, okay, well, now this has nothing to do with the complex numbers, and so I can do this actually over any field. And so Vey was the one who actually went through to defining this, and he's able to show that this makes sense as points on an actual variety. And of course, because you can add these divisors, it is an abelian variety. And there's a fixed map, which I'll keep calling alpha, between the curve and its Jacobian that just takes p to the formal divisor p minus p naught. And so, as I said, it's an abelian variety, and therefore the group of rational points is finitely generated, so it has a well-defined finite rank, and that's this number R that showed up from the start of the talk. Okay, so here's Chabauty's theorem. So it says if G is greater than R, then the set of rational points is finite. And the proof is p-adic and computable. P, I can basically pick any prime. Well, for Chabauty, I can pick any prime. If I want to do this computationally right now, at least you have to sort of assume that P is restricted by out of the finite set of primes with bad reduction. But the proof is actually extremely simple. It's in principle. So you pick a basis, as we said, of the G elements of the homomorphic differentials, and one knows that you get homomorphisms of the QP point of the Jacobian to QP, which are sort of integrals of these omega i's. And now you see here we have this is JQ is basically, well, it's kind of like a group of rank R. Kind of like a vector space of dimension R, but here we have I'm sorry about that. The inequality is in the wrong way. So G should be greater than R. So I have more homomorphisms than the dimension, than kind of like the dimension of the vector space. So what that means is, as I restrict to JQ, they become dependent. Okay, so that means I can pick linear combinations of these. Let's call it this L. So it's a homomorphism from JQP to QP, which vanishes on JQ. Now I just restrict, I just apply alpha. And I restrict to XQP. And so I take the point in XQP, subtract the fixed point X naught, P naught, and I apply this L, and I get a function into QP, and this one's going to vanish on XQ. So you need some data about this function that is nicely behaved, but it's really a local unitic function. It's even what's called a Coleman integral. Okay, so that's the, in essence, that's the proof. It's a very complicated proof, and it can made effective because I can actually compute all of these Coleman integrals. Jan Balakrishn's the prime person sort of implementing algorithms for computing Coleman integrals. Okay, so now I want to switch to discussing heights. And so I can start by saying that heights are something fairly old. They were developed by Vey and Northcott in the 1920s, and where Vey used them to prove the Mordell-Vey theorem. And what it is somehow a measure of complexity for rational points. And the definition is as follows. So first of all, I need to define what a projective space is. So again, this is in algebraic geometry. You could use somewhat fancier notions, but a projective, the nth projective space corresponds to the set of lines, so one-dimensional subspaces in the n+1 dimensional vector space over Q. Okay. And now there's the definition of the height of the point. This point x naught dot dot up to xn, and that's supposed to stand for the span of the vector x naught to xn as a point in PQN. So it's a finite one-dimensional subspace. And what you do is you do the following: you take this x naught to xn, and you go over all primes. And here I count the prime in infinity as a prime, and you look at the absolute value. And remember that we have this Q absolute value that corresponds to the divisibility by Q. And I compute this Qth absolute value for every Q, including infinity. And I take the maximum, and I take the product of it. And now there are two things to notice. One is that if I look at x naught and xn, there's a finite number of primes that are going to show up in either the numerator or denominator. So if I stay away from those primes, the absolute value is going to be 1, because it's when something is not divisible, or prime doesn't show up at all, then the absolute value is 1. So the product's only finite number of non-one values. So it is really a well-defined product. The other thing that one should notice is, right, I mean, two vectors x naught to xn could give you the same vector space. That happens if and only if one is a multiple of the other by some rational number, non-zero rational number. And here, what happens is that if I multiply all the x's by an alpha, then all of the absolute values get multiplied by the absolute value of alpha. And so the maximum gets multiplied by that. But now there's a product formula that says that the product of all the absolute values, including the absolute value at infinity, is 1. And that's fairly easy to see, because you see, if you take a number, and let's say for example that it's an integer, you write it as a product of primes. If the prime q shows up, the q absolute value is q to the minus r, but all the other ones are 1, but the one at infinity is q to the r. So this cancel out, and you just get 1. So this thing is actually well defined. And here's the simple example. You take, this is the standard height on P1, right? So you take the point AB, rational number AB. You think about it as in projective coordinates as A over B and 1. And now you can scale, because I said I can multiply by anything. So I scale by B, I get the point A dot B. Now I can and so now you have this formula, but now I can further say, well, if I can scale, I can always make sure that A and B are integers and they have no common factors. So I pick A and B to be integers with GCD 1. And in that case, you see the absolute value is always less or equal to 1. One of them is always 1 because there's no prime that divides both A and B. So the maximum is always 1 on all the primes except infinity. And so if I put A and B in that form, it's just the maximum of the absolute value of A and maximum and absolute value of B. And that's the sense in which the height gives you the degree of complexity of the number, right? So A the number a over b, its height is just how large is the numerator and the or denominator. Okay, so that's the height. Okay. Right now, when I gave the more specialized talk yesterday, I said that you should basically forget about this, all these standard heights, because there's a much better way of doing all of that, and that's the method of p-adic metrics and heights, which is due to Zhang, and there. So you start with the notion of a line bundle. So line bundle, sort of naively, you associate a line, so one-dimensional vector space, to every point on your algebraic variety. Right, and here's the relevant example. It's sort of the tautological line bundle of P and Q. Right, we said that P and Q was the set of all lines in n plus one dimensional vector space over Q. So the tautological line bundle says, okay, well, since this is just a collection of all lines, the line above the point is just the physical line that represents it. Okay. So now let's say that I'm on a line bundle over a variety over QQ. So in other words, all the coefficients of the equations are in this QQ. And defining things for the line bundle are also somehow in QQ. And then a norm associates to every line a norm, a usual norm, right? So it's a function with values in R, such that if I multiply by a scalar, I'm going to be picking up the absolute value, in this case, the Qth absolute value of the scale. And then what I want to do is I want to take a variety over Q and a line bundle, and I want to now go over all primes and look at the completion. So just take the same thing, but just think about it as a variety over QQ. And I make the definition that an p-adic metric just means that I associate a norm at every prime Q, and there's some technical condition which I won't go into that sort of guarantees that the height that are coming are going to be well defined. And so the height associated with an p-adic metric on a line bundle is just the following thing. I want to do the height at a point, and what I do is I pick a vector above the point, and I just take the product of all the norms in all primes, including the prime at infinity, of the norm of that vector. And again, because I have a product formula, it actually doesn't matter which vector I take. Because if I multiply by something, I pick up the product of the absolute values of all at all the primes, and it's just going to be one. And now it takes a second to go back to the example that we had before, and just do this on P1, even though it's true for Pn in general, but it's slightly easier to think about it with P1. So you look at the tautological line bundle, you look at the max norms, all right? Remember that the lines for the tautological line bundle were naturally embedded in Q squared. So you can look at the max norm in QP squared, basically, and just completely, in some sense, obviously, what I get when I do this procedure is I just get the standard height as I had before. Okay, so one reason to do all of this stuff is to get canonical. So I would say the following. The story is like that. So they invented, Northrop invented heights in order to prove the Mordell-Weil theorem. And the way that it worked then was they noticed that the height had some sort of a quadratic behavior. When you were working with an abelian variety or an elliptic curve, but it wasn't quite quadratic. It was quadratic up to something bounded, right? So if I took and it was quadratic in the multiplicative way. So if I took a point on the elliptic curve and I multiplied it by n, the height was raised to the power n squared up to some bounded quantity. And what Tate, who's pictures on the left side, notice what was that you could take this height and you could make it canonical. And it's sort of a very general procedure. If you have a function, so you first you take log, so it actually looks like an additive function a quadratic function in the additive sense. And if it's almost quadratic, you can make it quadratic by sort of averaging. So what you do is you take your point x and your height function h, and you look at h of 2 to the n x, and you divide by 4 to the n. And you take the limit as n goes to infinity, and all of a sudden this new function becomes quadratic on the nose. And that's actually a fairly easy procedure. Brilliance is just to notice that this is true. And then Zhang, who's pictured on the right-hand side, notice that instead of doing this on the global height, you could actually do this on the level of norms. And so, and then the same idea is applied, well, in fact, the same idea also sort of like the Tate idea, but then also this Zhang idea are applied to more general sort of dynamical systems. So there's a whole theory now of arithmetic dynamics where things of that sort are being used. So you take an endomorphism of your varieties. It's an algebraic function from x to x. And let's say that your line bundle L has the property that its dth power is isomorphic to its pullback by f. And then you can find a metric where this isomorphism is actually in isometry, so it respects the norm. And the way that you do this is simply by the following: you start with any norm, you pull back by f, and then you take the square root. That's a new norm on L, and then you repeat this until it converges. And it's fairly clear that this is exactly kind of the local version of doing the thing that Tate did globally. Okay, so and then somehow after canonical heights came into the scene in the classical world, they were used for things like the Gurion conjecture. And so people realized that there was a value to trying to get canonical heights. And as a result, there was work on p-adic height pairings. And we've kind of reversed the flow of things. And now we're going to go back and do a p-adic version of heights in general, and also a p-adic version of canonical heights. So, I mean, there's a lot to say about this. I'm not going to get too much into that because it's at some point it becomes rather technical. But people in my lecture yesterday can attest. After some technicalities, the whole idea actually becomes extremely simple. So there's a way to do the whole thing p-adically. And the main difficulty is that this averaging trick that I pointed out doesn't work p-adically somehow. So you have to use a completely different technique, but there is, as it turns out, a technique to do this. And our main application at the moment is to take an abelian variety, and you take the map, which is multiplication by 2. And then line bundlers somehow on abelian varieties have a sort of an eigenvalue decomposition. And the +1 eigenvalue. This is not with respect to 2, it's actually with respect to x goes to negative x. And so if it's symmetric, then it turns out that pulling back by 2 gives you the 4th power. But if it's antisymmetric, it only gives, should be 2th power. Sorry. I should fix that. This is 2, not 1, not 4. Sorry. And what this gives, so you run this procedure, you get canonical metrics, p-adic metrics, whatever that means, and so you get canonical p-adic heights. And the symmetric ones give you quadratic forms, and the antisymmetric ones gives you linear functions. And if you take something arbitrary, you can split it up to so the 2nd power into symmetric and antisymmetric. So what it gives you is a general quadratic function. And so you have quadratic Chabauty. And this is basically, in some sense, our hopefully simpler or significantly simpler interpretation of the work of Balakrishnan and Dogra. So I didn't go over that because that would be way too complicated, and in some sense maybe unnecessary, because now there's this significantly simpler explanation. I hope for that. So here's the method. Here's how to get rational points from that. So what you do is the following thing. You look at line bundles on the Jacobian LJ, such that as I pull back to the curve, they become trivial. Okay, and so each line bundle gives you a quadratic function. And let's say that out of these, I get certain functions Li that I had before. These were the functions that were used for usual Chabauty, but then I have new functions Hj. And this is still of dimension R. If I have more than R functions, I get a relation. Now, unfortunately, they are no longer linear, so it's not a linear relation, but it is some relation. So some polynomial in Li and Aj is going to be 0. Okay? And so now I can plug in an x in xq and push it via alpha to the Jacobian, and I get the following equation. So E of Li of alpha x and Aj of alpha x is 0. So that's some function. Now, unfortunately, it's not a function that extends to QP. It's the L's, as in the usual Chabauty, do extend to QP, but the H don't. The H are sum of a lot of terms somehow. It's like the classical thing. It's where it's a product of a lot of terms, and it doesn't extend to QP. However, because I chose these L's to pull back to the trivial thing, then it's almost true. What happens is that this function, when I take Hj and compose with alpha, I get a function which does extend to QP, and then up to some finite number of possible values. So you could think about it as being a function that takes a finite number of values, right? And so now what I get is the following thing. The set of rational points is contained in the union over all possible choices. So T1 should be in capital T1, T2 should be in capital T2, and so on. And then I plug in this function, which is the polynomial in the Li's and the HPJ plus this correction factor. And I look at the set where this vanishes. This is a subset of XQP, and this is and the rational points are contained in it. Okay, well, you can say, well, that doesn't quite sound convincing, because what's to prevent me from taking more and more H's? And it seems like I can just do this in general. Well, that's not the case. Of course, if I replicate the H's, I don't get anything, right? So there's clearly something that needs to be done. But the fact is that if the H's correspond to line bundles which are independent inside the Jacobian, or rather more the homology classes are independent, then in fact you get an actual non-trivial relation. And so that's Quadratic Chabauty. That's the thing that's going to give you rational points. And I should point out that this, in theory, well, I'll quantify what in theory is. This is computable.
Is it a union or intersection?
No, it's a union, because
so the more functions you take, the less information you get.
No, well, you see, I mean, I'm on a one-dimensional thing. I only sort of need one equation, right? One equation would suffice to cut down a finite number of things. The thing is, right, that it would sort of, I mean, here there's a condition, right, that there are more functions than R. That's the essential. That's the essential condition. If R was very big, then Chabauty would not be able to handle it. So it would seem like I could just take more and more height functions and somehow cover it, but it's not. I have to make them make them independent. And here you see, I have to account for the possibility that the other stuff that doesn't go into the HPJ, which is the local component in P, could be one of any possible number of values, right? And the usual thing, the usual application is that there's just somehow one J, right? So it's like the R equals G and one additional thing. But in principle, and then also the equation is much simpler, I think. But in principle, you could do that in general. Now, I just want to quantify what it means that it's computable. So we can write down what these HPJs are in terms of Coleman integration theory. So you can say that it's an integral, and then it's mostly just an issue of being able to compute this integral. And this is done by Balakrishnan. I don't know. I think she says she doesn't have an official code, but she has an unofficial code. So basically, this thing should be ready for, or almost ready for our actual applications. Yeah, okay, and I just wanted to say a few words about Kim's non-abelian Chabauty. That's the general framework where everything acts, and it's sort of in the same spirit. So what happens is that you enrich Chabauty's theory by iterated Coleman integrals. So these are, so you think of Li as being this kind of linear things, the HPJs as being the quadratic things. These are that's why it's called Quadratic Chabauty. But you could have more complicated Coleman integrals. That would be a very general thing. And then you have to replace the Jacobian by something called the Selmer variety, which is a complicated construction of Kim. And you have to replace the Abel map or the Abel-Jacobi map by so-called non-abelian Albanese map, which for some reason people started calling the non-abelian Kummer map now. And the conjecture is that if you kind of go sufficiently high, so you take a sufficiently complicated iterated Coleman integrals, eventually there'll be a relation, and it will give you a non-trivial function that vanishes on rational points. The difficulty in all of this is there's sort of like a theoretical difficulty figuring out why it's true that there will be some relation, and then even more difficult is to actually find this relation where it exists. So like the quadratic case, the problem of finding when it's going to work is just this condition that the G is greater than R, or the G plus the rank of the also variable -1 is greater than R. So it's very clear numerically, but actually finding the correct function would require something more. For example, require computing height pairs on the Jacobian and things like that. So then in the more general case, it's far less clear, but at least based on sort of standard conjectures, Kim shows that this will somehow always work. Okay, yeah. So that's what I wanted to tell you. So thanks a lot for your time here and elsewhere.
Thank you very much for the very beautiful talk. And so let's see if there are questions from here or from the chat. Well, I had a curiosity about the first thing you said, trying to solve x cubed plus y cubed equal z cubed equal to something. When is the box determined because you know that the height of the point must be bounded by something? Or?
I think it's just not just the box. So in other words, it's an intelligent search in the sense that you kind of restrict to some subcurve or subsurface.
Okay.
Right. So there's you already know that there will be some relation between the x, y, and z. And after that, I'm not sure that. I think that you just set a computer to look for a particular range, and so the math somehow in this is to actually look for the particular relation. Otherwise, you just don't, I mean, you can't deal with a sufficiently large block.
Can I ask about the slide, quite at the beginning where you explain Chabauty's method?
Okay,
the first
sure.
time.
Yeah, let's see. Oh, yeah, I think I should intervene.
If I can shrink it.
There's an X on the right.
Yeah,
I wanted to
yeah, there's a. Oh, okay.
try again.
No, I already
Even
went past
before
that.
that.
Yeah. No, before that?
Yeah, yeah.
You didn't
the
know-
very
you don't- this
beginning,
thing?
the very beginning. Even
Oh,
before. Oh, no, yeah,
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 this-
no,
this one.
sorry, that slide, yeah.
yeah, right.
All right, so here, assuming that the rank is greater than G, and you say then there's a linear relation, the Li will be dependent on JQ.
Right.
But in principle, that's something you could argue over the complex numbers as well, right? That, right, I mean, those are functionals, it's the same thing. So what role do the p-adics play here?
Well, the problem, okay, I mean, remember, this thing, you could sort of think about these L, well, the combination of all of these L's as sort of the analog of the Abel-Jacobi map. And the Abel-Jacobi map in the classical case, what goes not into C to the G, but rather into sort of C to the G mod the lattice, right? And so in that case, you're not right. You're somehow not at a vector space. So that's why it's more difficult to find relations, right? So I guess
The C point of the Jacobian is not, you don't tensor with C, right? To calculate the C point of the Jacobian.
sorry.
So like, the point is that you have the rank of the Q point, but there is a map from the Jacobian to C, but you are not just tensoring the rational point with C. It's more complicated, the construction. And this G essentially tells you exactly what is, that the Jacobian is this C to the G modulo some relations, which is a lattice by another argument, no?
But isn't it also JQ, if you take the topological closure as still rank G, while in the complex topology it can be dense, even if the rank is small.
Yeah.
So you don't get any, even if you would have functions, you wouldn't get any. And you can have a rank one group in a torus that is dense. So.
Okay, if there are no more questions, let's thank Amnon again for the talk. And for Guillermo, I think we can stop.